I'm Lisa Freehill. I am the co-chair with Peter Meyer of the Government Advances in Statistical Programming Conference this year. Welcome, welcome to everybody who is attending today and tomorrow, and to all of our awesome speakers. I'm going to go over a few quick rules of the road, so to speak. You know, so far, I'm sure we've all kind of had enough time on Zoom to know how these things sort of operate. We do have a detailed program available, and you can take a screenshot to access it using the QR code up above. You're going to be muted as attendees. If you want to ask a question, please enter it in the Q&A box, and then the session chairs will be monitoring that to queue those up for speakers. There's going to be additional information will be placed in the chat, and if you need to, you can enable the closed captioning in Zoom. We've also set up a couple of Jam boards so that you can share information with each other about events that are coming up, as well as jobs that might be available. We've got a very packed schedule, and so papers are going to have 12 minutes each, lightning talks will have 6 minutes each, and each session just has a little bit of time at the end for Q&A, but the session chairs will moderate that. If you've got any problems, please reach out to Peter Meyer or myself at those email addresses, and we'll see if we can get that all set up for you. So as I mentioned, the agenda is pretty packed. We've got 5 paper sessions, 5 lightning talk sessions. There's a total of 21 papers and 17 lightning talks. Plus we have 2 really awesome plenary speakers. So I'm going to turn it over to Nathan now to talk a little bit about CSPAS.
All right. Thank you, Lisa. I wanted to put in a quick word about the Federal Committee on Statistical Methodology and who we are, the interest group in computational statistics and production of official statistics, or CSPAS. The national statistical system in the United States is decentralized. And so a small office called the Office of Information and Regulatory Affairs within the Office of Management and Budget is really tasked with setting and coordinating consistent national statistical policies. And so to that end, they created the FCSM in 1975 to be a resource to OMB and the federal statistical system at large. And so today there are many subcommittees and interest groups that provide technical guidance on a variety of topic areas. This interest group, the CSPAS, was created in 2018 out of several recognized needs. The need to take stock of rapidly changing methodological and computing landscape relative to our available computing infrastructure, to try and foster conversation between statisticians, data scientists, and agency IT professionals, and to share knowledge between federal agencies on matters of recruiting, training, and equipping staff with practical computing skills and appropriate computing environments. This conference, GASP as it's now known, is in its 5th iteration, and it is one of the ways that we do this, that we share information across agencies, and it's one of our important deliverables to FCSM. But it's not all that we do, and I want to mention just a few of the past presentations that we've had at our bi-monthly CSPAS meetings. Jenna Truman of the Bureau of Justice Statistics presented a total survey error approach for monitoring and maintaining quality of the National Crime Victimization Survey in the era where face-to-face interviewing became impossible due to the COVID pandemic. We recently heard from Wade Petty and Amanda Lindecker of Bureau of Economic Analysis on appropriately supporting their agency of a little over 300 employees to use Python in desktop production environment for some of their routine duties at BEA. We've also had presentations by Brandon Kopp of the Bureau of Labor Statistics, who provided a briefing on to the group on the uptake of the government-wide adoption of a recently created federal data scientist job series, and comparing and contrasting that with other job series families, including statistician, mathematical statistician, and say operations research. If you have interest in conversations like that, and if you have a .gov or .mil email address, I'd invite you to reach out to either me or Wendy Martinez and consider joining us at one of our routine meetings and propose topics of interest that would serve you and your agencies well. Next slide, please. This is a real labor of love to host a whole conference for $0. And so it means you're going to your friends and really asking them to be generous with their time and resources. Here you see a committee, an organizing committee of 11 from inside and external to government. And I won't list them all by name, but I do want to extend a sincere thank you for their time, their creative energy. And I'd encourage you to try and connect with them virtually or next time you see them and extend your thanks to them as well. They've been really successful in helping us put together this year's program, and I think there's a lot of good content coming our way. Next slide, please. And of course, I want to extend some very special thank yous to the people who have provided us resources. Thank you to Donna Lalonde and the American Statistical Association for granting us access to this Zoom webinar platform and supporting the advertising for the 2023 conference. Thank you to a chapter of the American Statistical Association, the Washington Statistical Society, for their past and ongoing support of GASP and for hosting presentation materials in the past. And I also want to highlight a couple individuals, Jennifer Ortman and Mark Prell, for some of their webmastering of the recently created fcsm.gov website. It will be our intention to collect this conference presentation materials and link recordings of today's event through the FCSM CSPOS website and YouTube channel. And before we go on, I also want to acknowledge the contributions of the R Consortium through their R Govies interest group, as well as some individuals, Jun Yan and his colleagues at University of Connecticut, for suggesting multiple journals that could support a special issue for this instance of GASP. And so thank you, June, and the Journal of Data Science. To our presenters, be on the lookout for information, an invitation to submit articles for consideration in a special issue of the Journal of Data Science. With that, I'm going to turn over the floor to my co-chair, Wendy Martinez, and welcome you all to GASP version 5.0.
All right, thanks, Nathan. So I'm really terrible at introductions, so I'll just give this a shot. But I'm really pleased to introduce a colleague, Cynthia Rudin. She is the Earl D. McLean Jr. Professor of a lot of things: computer science, electrical and computer engineering, statistical science, and a lot of others. And Cynthia, is that really all together? You're part of all those departments?
Mostly secondaries, but okay. Yeah.
All right. But it's really interesting to see them sort of hooked together like that. But maybe more exciting, at least in my view, she's also the PI of the Interpretable Machine Learning Lab at Duke University. And she's done a lot of work in interpretable models, black box algorithms, and so on. So be sure to check out her website for more information on her achievements there. Her research focuses on machine learning tools that help humans make better decisions, mainly interpretable machine learning and its applications. She's a recipient of many awards and honors, and it's really exciting. She's been the recipient of the Squirrel AI Award for Artificial Intelligence for the Benefit of Humanity, which I believe is given by the Association for the Advancement of Artificial Intelligence, or AAAI. I think this was in 2022, which is the most prestigious award in the field of artificial intelligence. And so you could think of the Nobel Prize and the Turing Award. And in fact, it carries a $1 million prize. So that's amazing for a fellow statistician and data scientist to receive something so prestigious. So with that, I don't want to take up more of, I want to give Cynthia a lot of time to talk about an exciting topic that's near and dear to my heart, and that's dimensionality reduction. So Cynthia said if there's questions of how did you call it? Like understanding,
Yeah.
Urgent questions for you to understand the talk at a particular point, feel free to, or clarification, that's it. Feel free to put them in the Q&A and I'll interrupt Cynthia. Otherwise, we will hold questions until the end. So I'll give the platform to you, Cynthia.
All right. Okay, there we go. Okay, great. All right, so I'm going to talk about dimension reduction today, where the goal is to take a data set, which is in higher dimensions, and project it down into 2 dimensions so that humans can understand what is actually in the data. All right, so many of you may have heard of TSNE or TSNE, which is the most famous dimension reduction algorithm. So TSNE, the input to it is high dimensional data, the output is low dimensional data. And it preserves something or other. We're not exactly sure what. So it's maybe supposed to preserve the graph structure of the high dimensional data or local neighborhoods or the global structure. It's not exactly clear. Dimension reduction, though, it allows you to really understand what high dimensional data actually looks like. And it turns out that it has quite a lot of important use cases, particularly in biology, because people really want to know what structure is in their high dimensional data. All right, now I had the good fortune to listen to Martin Wattenberg give a talk on dimension reduction several years ago. And he pointed out that some of the dimension reduction algorithms, in particular TSNE, doesn't do exactly what you kind of expect it to do. So here's a data set, which is just 2 Gaussians. And so it's already in 2 dimensions. So the dimension reduction algorithm has to do basically nothing. But it doesn't, it actually does something. So if you take TSNE and you fiddle with it, it has a mysterious parameter called perplexity, which is fairly perplexing what it actually does. But anyway, if you adjust that parameter, you can get completely different results. Like, it doesn't really look like this, right? And if you adjust it too far, you get these like stringy things. And then here it just looks like a big giant mess, which it's not, it's 2 things. And then, in fact, cluster sizes in a TSNE plot don't mean anything. Like here, there's these 2 clusters are different sizes. Again, the algorithm has to do nothing, but it does something. It's very misleading as to what's actually going on. So I think this is really, problematic because the biologists use these methods to figure out what's going on in biological data. And these problems are not supervised, so you do not know how to set the parameters. And you don't know what the data really look like in high dimensions. So you might easily get misled into thinking the data is one thing when it's actually not. Now, I ended up leading this working group at SAMSI, and Yingfan and Haiyang and Yaron and I, we decided to just devote a semester trying to understand this topic. And here we are still working on it 4 years later. Anyway, so this is the mammoth, and the mammoth data set is a 3D data set, and I want to project it down to 2 dimensions, okay? And I want to use all different algorithms to do it. So here's what happens if I do that. So if I use TSNE with different perplexity values, you can see that it just doesn't do a good job. In fact, it really looks like TSNE dismembered the mammoth and ran it over with a steamroller or something. And that's true kind of no matter what perplexity value here you use, although this one looks a little bit more like a chicken than like a mammoth. This is UMAP, which is supposed to be an improvement over TSNE, but it still kind of looks like a frog that's been gone under a car wheel or something. And then here, large Viz. Large Viz unfortunately separated out the mammoth's legs. That's quite misleading. Doesn't look like a mammoth anyway. This is TriMap, which did a great job preserving the mammoth's global structure. And then this is the method that we constructed, which is called PackMap. Okay, so this one also really nicely kept the mammoth's kind of global structure. Okay, so that's a 3-dimensional data set. Let's switch to a much higher dimensional data set. This is MNIST, which is handwritten digits. So you've got a couple hundred dimensions. Each dimension is a pixel in, this pixel space of these handwritten digits. And then if you take that and project it down using the different methods, TSNE does what it always does, which is fills up the space. UMAP did a beautiful job on this particular data set, separating out the different handwritten digits. TriMap was a disaster. It smushed all of these together. And if I didn't tell you the ground truth, which are these colors, you would not know that these are 3 separate handwritten digits. These are all smushed together. And then this one, I don't know. Anyway. And then this is our method, okay? So what I'm trying to show you is here, our method does really well, even if even in these two separate cases where kind of global structure mattered in the first one and local structure matters in the second one. All right, and also I should point out that TS&E made a terrible mistake here that you might not have noticed, which is that these are just one digit and it separated it into two clusters and pulled them apart, which that shouldn't happen. They should be together. Like that's this cluster here and this cluster here. So we already know that this is a mistake. And then over here, it split this into two different clusters as well. It's only one cluster. All right, so you can see that a lot of these methods have a lot of trouble with the balance of preserving local versus global structure. Okay, so what does that mean? So when I say local structure, I mean like the local neighborhood graph, like who are your neighbors? Who are your nearest neighbors? And then when I say global structure, I'm talking about kind of larger structures in the data, like relationships between clusters or respecting relative distances between points in high dimensional space. And you can think about this kind of like going from like a global algorithm to a local algorithm. So for instance, PCA, principal components analysis, is like the quintessential global algorithm that knows nothing about local structure here. Whereas TS&E is really all local all the time. UMAP is local, and then is mainly local. And PACMAP, as it turns out, and I'm going to convince you of this during this talk, is that it does both local and global structure at the same time without sacrificing either one. So just to give you a little bit of a history of the field of dimension reduction, it really started out with these kind of global methods like principal components analysis. And then around the year 2000, people started introducing these kind of local methods that try to preserve sort of distances, right? And the problem with preserving distances from high dimensional space to low dimensional space is that the distances are almost all the same. And so it just didn't work. And so they switched in around 2003, which was like the turning point here, to really kind of like preserving neighborhoods. And the first method that did this was SNE, which had a crowding problem where all the points would sort of blop on top of each other, which was not very good. But then TS&E actually figured out that no, we can actually preserve neighborhoods. And that's what we should be doing. Now, of course, the problem with this is that they don't actually work like they're supposed to, which is what I showed you on the previous slide. So then this literature sort of sprung up, which showed you kind of how to fiddle with the parameters of these algorithms to make them work. Now, if these algorithms worked in the first place, none of this literature would need to exist, right? Because, it's just really hard to tune the parameters to get global structure out of these methods. And so that's why this whole literature exists, because the methods don't really work. All right, so the first thing we did was to look at the equations, like the loss functions that these algorithms optimize. But it was almost like nothing was in common when you actually look at the loss functions. And we just got completely confused. We couldn't find anything in common with them, and we didn't understand them. So we said, let's just start over, forget about these equations that we don't understand. And we'll just start from something very simple, okay? So we'll start from just placing attractive forces and repulsive forces. So if you have 2 points that are close in the high dimensional space, they should be attracted together in the low dimensional space so that they're close together when you do the dimension reduction projection. And then we should also have repulsion. So if you have 2 points that are far away from each other in the high dimensional space, they should also be far away in the low dimensional space. So if they get too close, we should push them away. Okay, and then as soon as we set this up, we said, great, let's just optimize something like that. And it turns out that that just didn't work at all. It's just not enough, okay? It's not enough forces. So here's why. So if you have just two loss terms, one attracts neighbors, one repulses faraway points, you can basically send this loss function to 0. You can perfectly optimize these things, and your dimension reduction plot will look like crap. Okay, so here. So this is an example of a two-dimensional data set. It's a bunch of points along this kind of curve. And then if you minimize this thing, and again, all the method has to do is leave it alone, but it doesn't, you could get something like this. which completely minimizes, this objective, but doesn't preserve global structure at all. So in fact, all the neighbors are next to each other. All the further points are far away from each other. Anything far here is far here. So we've done a perfect job on this loss function, but we just didn't do this right. And by the way, this is actually a result of UMAP, right? So UMAP actually doesn't preserve global structure. All right. So after a huge amount of experimentation, we figured out kind of how to actually understand preservation of local and global structure. And what we found was that certain specific properties of the loss function are important for local structure, and the choice of which graph components to exert forces on is important for global structure. So what do I mean by that? So all of the methods, all of the dimension reduction methods, minimize something that looks like this. So it's a sum over graph components. So this could be like pairs of points, or it could be triplets of points or something like that. So just components of the high dimensional connectivity neighbor graph, right? And then some kind of weighted loss on that graph component. So it might be like pull these 2 points together, push these points apart, whatever. All right, now to get local structure, you need to worry about what these functions are. And then to get global structure, you need to worry about what you have in this sum. And so these are two different mechanisms to handle local and global structure. And so that's why we're going to be able to handle them both at once. Okay, so for local structure, we need to talk about the loss function. We're going to talk about local structure first and then global structure. But as I told you, I can't really write down an equation that is similar to all the loss functions because all the loss functions have totally different functional forms, right? They look like that, which, like trying to find something in common with all these crazy functions, that's just not very fun. But we did figure out a way that all of these functions are similar. And it doesn't involve equations. It involves a figure. And that figure we call the rainbow plot. So the rainbow plot is a way to visualize and understand the loss function. Okay, so let's say we take a triple. We have I, which is I, that's me. Okay, I. And then J is my neighbor. So that's a point that's close to me in the high dimensional space. And then K is a further point. So this is like my enemy in the high dimensional space. And I want to keep them away. I want to keep my enemies away when I project down. So I have this triple here, I, which is me, J, my friend, K, my enemy. And the loss function, what should it look like? So where do you want to be here? So let's see. So we want our distance to our neighbor to be small. And we want the distance to our enemy to be large. So what we'd really like is to be kind of up here somewhere, right? So this is where the loss function is minimized because my friend's close by, my enemy's far away. And then where I really don't want to be is over here. Because here, my enemy's really close to me and there's no friend here to defend me. Okay, that's obvious. What about this? So here you've got a friend and an enemy who are close by. Is that good or bad? And it turns out the answer is it's bad. Anytime you have your enemy close by, you get upset. The loss function's large. And then what about over here? So here your friend and your enemy are far away. Is that okay? And the answer is it's actually okay. So let me fill in the rest of the rainbow plot for you. So anytime your enemy's close, that's bad. If your enemy's not close, you really kind of want your friends close to you. But if they're not there, like it's okay, whatever. Okay. Anyway, so I'm going to just fill in the whole rainbow plot here. This is a rainbow plot, and then this is just the magnitude of the gradients. And then you could say, okay, well, which algorithm, is this TS&E or UMAP or what is this? And the answer is, I don't know, because they're both the same. So even though the equations are completely different, the rainbow plots for the loss functions of these algorithms are very similar. So this is TS&E, UMAP, and PACMAP, which is our method. The one that isn't similar is TriMap, but as you know, TriMap does not do well with local structure because that's why these are crammed together. So it's kind of interesting that the one whose rainbow plot is different just doesn't do a good job at local structure. All right, so so what we did when we figured all this out, we created a set of principles for what a good one of these rainbow plots looks like. And we wrote all of these down. We like formalized it all in terms of, it's all in terms of differential equations, believe it or not. It's like derivatives and limits and so on. But basically all of the ingredients of what a good loss function should look like for preserving local structure, it's all like written out formally. Like the gradient should go up. It should be a large, large gradient right here to push the enemies away. You should pull your friends close, but if they get too close, you should ease up the gradient so you don't have a crowding problem, and so on. So it's actually kind of a really nice kind of like foundational kind of principles for what a good loss function looks like. All right, and then from there, we tried, and before we realized these principles, and before we realized what these rainbow plots should look like, we tried to derive a whole bunch of new loss functions that didn't work. And I'm going to show you the failed loss functions and their rainbow plots. So those kind of look like this. As you can see, it just didn't work. The dimension reduction results are crap. And by looking at the rainbow plots, you can see exactly why they didn't work. Like these rainbow plots do not look right. And you can even pinpoint exactly which principles are broken of our set of principles. Like, there's no getting rid of enemies here, and it's, we're going up, we should be going mainly to the left, and so on and so forth. You can kind of highlight where in the rainbow plot the method went wrong. Anyway, so we're not using any of those loss functions. All right, so once we had the knowledge of what a good loss function's rainbow plot should look like, we could actually design a loss function for PacMap that is much, much simpler than the loss functions of TS and UMAP and TriMap. So PacMap's loss goes like this, and I can just write it right down here, okay? So I'm just going to define the distance between 2 points in the low dimensional space as Euclidean distance plus 1. I'm adding the plus 1 so I don't divide by 0. And then PacMap has 3 terms, one for attracting your neighbors and one for pushing away your further points, and then there's a third term that I haven't told you yet. Okay. All right. So for the attractive loss term, so that pulls your neighbors together, and the repulsive loss term, they look like this. Okay, just like that. So if you have so if you take a look at this term is very happy when distance is small. And this term is really happy when distance is large. And so you can see that it's pulling your friends close, pushing your enemies away. Okay, so it's very, very simple, much simpler than all of that. Okay, and yeah, this completely handles local structure. This is exactly how PacMap deals with local structure, and that is what produced the rainbow plot that I was showing you for PacMap. Now, the third term, I haven't told you yet, deals with global structure. So for global structure, as I mentioned, we have this problem that if you just do attraction and repulsion, it is not enough, because you can get, you can do a great job at attraction and repulsion of neighbors and faraway points, and you just still don't get global structure at all. And so it's just not enough forces, and you have methods like UMAP that are completely nearsighted. And in fact, if you plot UMAP's forces over distance, you can see that both the attraction and the repulsive forces kind of fade very quickly over distance. And that basically means that UMAP is kind of nearsighted. Okay, let me pause for a second and answer some questions. So let's see here. Okay, Y10. Okay, so Y10, guess what? It doesn't even matter. All those parameters, it doesn't really matter what the values are. We have a 10 and a 1 here, but it doesn't matter as long as you kind of get this kind of general attractive force and general repulsive force. Doesn't matter. And that's what's really nice about this. It's just sort of like an idea, and the actual parameter values don't really matter because it's like robust to whichever values you pick as long as you don't go completely crazy. Okay. Yeah, I can't quite figure out what that other question is about. I'll answer that one later. All right, and some resources on this technique. I will show you I have the link at the end, but you can just Google PacMap, and we have a website, and we have, like there's plenty of tutorials and stuff. We have something like 270 GitHub stars, so lots of people are using this technique. Okay, all right, so let's talk about global structure here. So as I mentioned, yeah, we have the fading of forces, which is not good, okay? And so Yingfan had this idea, which was to attract mid-near points to try to get global structure. So in other words, if you're here, then maybe instead of just pushing away all the further points, maybe you could kind of attract some points to you that are kind of should be vaguely close, like they're not your neighbors, but they should be at least in your kind of like vague sphere, okay? So your slightly larger sphere than the neighbors. And this actually really helped a lot. And it actually made totally the difference between not having global structure and having global structure. So I can actually put up all of PacMap's loss terms now. So you have the attractive term and the repulsive term, and we talked about those. And now the last term is a mid-near pairs term, which has like a very gentle attractive force on points that are mid-near. They're not near, but they're like a little further away. And to get those mid-near points, you sample 6 observations from the data set, and you choose the second closest of the 6 to be your mid-near point, and you just pair it with I, and you just give it a gentle pull toward you. And so this 10,000 here is just gentle pull. And again, the parameter values don't really matter. It's the idea that really matters. Now, the mid-near points have a huge effect. So for instance, if you take these 2 data sets, which are 3D data sets, this is without any mid-near points. This is with just 2 mid-near points. And then you can even get global structure with just 2 mid-near points. And here's the mammoth, no mid-near points, and here's 2 mid-near points. So it really makes a huge difference. Okay. So yeah, so now I've explained to you what makes dimension reduction algorithms tick. And so we designed PacMap, but then we ran into this issue after we designed it that we could not figure out how to evaluate it because, you know, this is unsupervised, so it's not clear how to evaluate it. So we thought about it and we decided that it was worth our effort to think really carefully about this. And so we ended up writing a whole paper on how to evaluate dimension reduction algorithms. We did it specifically for transcriptomic data, but the evaluation is a general evaluation. And we proposed 5 different types of evaluation. So local structure evaluation, global structure evaluation, sensitivity to parameter choices, sensitivity to preprocessing choices, computational efficiency. So those are the 5. And PacMap does really well in all of these metrics, but I'm not a big fan of showing tables in talks. So I'm just going to do a bunch of demos. All right, so I've already showed you the different methods on the MNIST data set where local structure is important. And all of these methods do well in local structure. So even though there's some global structure mishaps over here, it still does well in local structure because if you drew like a decision boundary around each of these, you would see that that decision boundary would classify the points from different class correctly. So they all do well in local structure in our local structure evaluation method, not so well in global structure. And then here, this is the mammoth again, where global structure is important. And only a couple of these methods do well, only these do well. And to evaluate that, you'd use triplets and say, okay, this is closer to this in high dimensions. Is that relationship preserved in low dimensions? And so here, only these 2 would do well. And then here's kind of a bigger chart with more of the same thing. So this is the coil 20 data set where you've got like kind of these kind of rings, these kind of coils. And then you've got also, this is the coil 100 data set where it's just more coils. These 2 are very difficult data sets to work with. This is MNIST again. This is fashion MNIST, which is like purses or handbags or something like that. Okay, this is the Postal Service data set. This is, you know, just handwritten digits again. News group, nobody gets the news group right. News groups, I think they're all just interconnected with each other. And so, you know, just really hard to do it. This is the S-curve with a hole. And again, this is a global structure one. So these other methods don't do so well. Now, this one's a mouse RNA-seq data set. So the issue here, this is really important. So a biologist might see all of these clusters in this data set and get really excited and try to actually spend resources to explore those clusters, but they're probably just phony. Oh well. Anyway, this is a peripheral blood mononuclear cell data set. And this figure was done by a student working with us from Germany, Carla. And she colored this data set in 3 different ways. So she colored it by cell type, so you can see why these clusters are connected to each other, because they share this kind of match by cell type. But these 2 pieces are separate because they're separate experiments. And then when you color by method, you can understand why these 2 are kind of in their own kind of area up here. And if you did the same experiment with UMAP, the plot doesn't look nearly as clean and tidy. It's just not as nice in my view. All right, so let's keep talking. So I want to talk about sensitivity to pre-processing. So here's a case where a lot of people, if you're using very high dimensional data, what you would probably do is project that data onto the first 100 or so principal components, and then from there run dimension reduction. Because if you just use dimension reduction straight from like thousands of dimensions, it doesn't work very well. So it would be computationally inefficient. So this is what most people do. They project first using PCA, get rid of all the junk, and then just do dimension reduction. And this is measuring sensitivity to the number of principal components you reduce to before doing dimension reduction. So here's a case where if you do TS&E for different numbers of principal components, it's like together and then separate and then together and maybe a little separate, but here. And then UMAP completely separated this cluster out over here. TriMap was completely consistent because TriMap does really well. It's very consistent in global structure. And then PacMap handles both, again, very consistently because the mechanisms are separate for local and global structure preservation, so it can handle both. And the last analysis is runtime. And so I'm going to show a table. Sorry about that. But it's a very easy to read table because PacMap is just much more efficient than everything else because its loss function is just much, much simpler than everybody else's loss function. And I showed you what it was. It was just those 3 terms. And yeah, that's it. All right, so I want to finish up with a couple more applications. So let's talk about name ethnicity classification. So this is a type of problem where, let's say that you're a bank and you are handing out like loans and you want to know whether your loan decisions are fair, but you're not allowed to collect ethnicity or racial information. So what you might do is just look at people's names because you have the name data, and you might try to estimate their race and then try to figure out whether your loan decision-making process is actually fair. Okay, so we developed this method for this problem called Ethnicia, and it uses a kind of voter registration data in the United States. And we developed a set of features that are useful for predicting ethnicity from a name. And we projected that space down to 2 dimensions with PacMap. So what you can see here is that you've got different nationalities of names in this dimension reduction plot. So here are Black names, these are Asian names, these are Hispanic names, and these are white names. And one interesting thing is that you can see, so again, this is voter registration data. So you have kind of like this is from like some states in the United States. And what you see here is this interesting kind of mix of Black and white names, which are very difficult to tell apart because a lot of slaves took the names of their owners. And so you get this interesting mix of names. So yeah, so it's pretty cool to kind of see the space of names kind of put down in this way, projected in this way. Okay, so let's switch to EEG monitoring. So for the last over 10 years, I've been working with a doctor who works in critical care medicine, and he was interested in looking at in creating an interpretable neural network for EEG monitoring. So this is where you put like monitors all over someone's head, and you're trying to monitor the electrical signals in their brain. So we built this interpretable neural network, and then we wanted to project the last layer of that network down using PacMap so you could kind of see what was going on. So here, these are different types of EEG signals. So seizures, LPDs, GPDs, lertogertis, these are things that occur in one side of the brain or the other or in both sides. And then seizures obviously are like, that's what we're trying to prevent by looking at these other types of kind of lower level signals. And the interesting thing about this PacMap plot, other than the fact that it looks like a really funky sea creature, is that it shows that there's a continuum between different types of EEG signals. And this kind of hypothesis that that these different types of signals were sort of had some overlap, that there was a continuum between them, is something that doctors had a hard time kind of formally seeing, right? They sort of thought maybe this was true, but then by viewing it this way, you actually see the continuum. And the doctors have been having a lot of fun walking between the different tentacles of this strange creature to see the different types of EEG signals kind of merging into each other and go walking along that continuum. And they're actually using this to help train neurologists to understand kind of the EEG the sort of domain, the space of EEG signals. Okay, so the last one I'm going to talk about is an application to the Explainable Machine Learning Challenge dataset. This dataset came from FICO. It's a lone decision dataset. We've been working with this dataset ever since it was released because we entered this challenge in 2018. Now, I want to point out here, so the name of the algorithm, PacMap, it actually has like it actually stands for something like principal approximately controlled, some manifold approximate, whatever, something. It actually has like a name. The students named it. And I was thinking, okay, well, I'm not sure I like the name. It's kind of a silly name. It sounds like Pac-Man a little bit. But, the students named it, and so I let them keep the name, right? And then it was only a few years after that I was talking to Yigfan, and I said, hey, could you please give me a PacMap result for the FICO dataset? And she sent it to me back that same evening, and I looked at it, and I said, no way. There is no way that PacMap produced this. And she's like, yeah, no, it's actually, it did. What are you talking about? And I looked at it, and I was like, there is no way that PacMap produced Pac-Man on this FICO dataset. And anyway, so she said, no, but Cynthia, this has actually happened. There's actually a technical explanation for this. There's some like structural missingness in the data. This is like data that's, it's missing not at random. So the missing data is all in one area. And then you have like this area, these guys are people with higher value of the external risk estimate, which is a really important feature for predicting when in this data set. And then, I was like, okay, it's actually sort of mimicking what we see in our machine learning models. But anyway, I find this kind of exploratory data analysis really useful because it really tells you something about the clusters or like the manifold structures within the data. But it is really hard to take this particular result seriously. All right, so just to summarize, I talked about what makes dimension reduction algorithms succeed or fail. And specifically, I talked about the loss function, which gives you local structure. And then the loss function should obey the 6 principles that give you the rainbow plot, okay? And the rainbow plot allows you to compare across algorithms, even if their equations are completely different from each other. And yeah, there's our lovely, perfect rainbow plot. All right, and then for global structure, I suggested forces on non-neighbors and specifically mid-near pairs so that you can kind of have a broad general attraction for points that should be close by. I presented the PacMap algorithm, which has a very simple loss function involving only 3 terms. And it preserves both local and global structure through these 2 different mechanisms. And it runs very, very quickly because of its simplicity. And yeah, hopefully it'll give you some information that you can glean about what's actually in that high dimensional data so that you can be a responsible decision maker. Yeah, and so here are the papers. This is the PacMap paper. This is the evaluation of dimension reduction paper, and then this is the GitHub repository. And we also won an award just this year from the American Statistical Association for the PacMap code. All right, thank you very much.
Oh, thank you, Cynthia. Yeah, I'm glad you mentioned the John Chambers Award. That's another, in my opinion, fairly prestigious award. Are you going to present this at JSM this year then?
I'm presenting a tutorial at JSM this year, so I don't know if my students are. I think my students might be presenting it. Yeah.
Yeah. Well, anyway, I'll be there and I'll be on the lookout for it.
Well, I'm always happy to present this. I mean, I love this particular topic, so yeah.
Well, me too.
Yeah. But I'm doing a tutorial at JSM on just general interpretable machine learning. So yeah.
Well, thank you. Well, we have some questions. I have one quick question, but I'll wait till the end. So we have maybe about 10 minutes for questions and answers. So do you want me to read the questions or do you want to read them?
Okay.
I don't know how easy it is for you to see them.
I can see all of them. I'm just having trouble figuring out which ones I want to answer first.
Okay.
Okay. Okay, let me go. Let's see. Yeah, I can't figure out this question here. How does this technique handle missing data? So remember, what you need to run a dimension reduction technique is a distance metric, right? You need to know how do you compute distances in the space. And so if you have missing data, you still need to figure out how do you what is the distance metric that you're going to use when you have a missing variable or something like that. So for instance, with the FICO data set where we do have missing data, those specific data points are they have encodings so that you can handle it as it's like a flag for this variable is missing, and then it gets put into a Euclidean distance with the data. So it's not really about, how do I say this? Like you as the user need to determine what that distance metric is, and you have to figure out how to do it with the missing data. Okay, and then imbalanced data. I don't really know what that means because, it's not supervised. So, no, okay. I'm thinking of cases where one class is broken into small isolated clusters entirely surrounded by another class. Oh, okay. So we have a bunch of really like crazy data generation processes that we're using to test these methods. And so sometimes it's like one big cluster, and then within that there are like I don't remember the name of it. It's like MIDI clusters and then mini clusters within those clusters. And so you can see this like hierarchical structure of these clusters. And none of the methods do amazingly well on that kind of crazy hierarchical process. And we have that in our papers too. We like presented these kind of maniacal data generation processes with that. So I think there's still work to be done in dimension reduction. I think that your question is sort of, right on point there. Okay, what is the sensitivity of clustering structure of hyperparameters to the loss function? That again, another really good question. That's exactly one of the evaluations that we propose in our evaluation of dimension reduction paper. Like if your method is very sensitive to like parameters, you've done something wrong because there's no way the users can know how to set the parameters. So you really want the method to be as insensitive as possible to parameters within a reasonable range. And if you have a method like UMAP, where its global structure basically just comes from running PCA initially, and then just it assumes that everything is fine after that, then the problem with that is that the global structure can be very sensitive to the parameters. And so luckily with methods that control global structure, like TriMap or PacMap, it's pretty robust to parameter choices. So yeah, that's a good question. And that's something that we're still kind of like still working on, because there are some of these genetic data sets where it's really hard to get the cluster structure exactly right. Okay, and then would it be reasonable to add a fourth term to the loss function on mid-far points? I don't see why not. In fact, we keep running through our meetings saying, oh, we should have a whole continuum of loss functions for the different levels of farness. And my students are like, oh, you don't need it. So I don't know. I think what you're proposing is totally reasonable. I don't know which problems it would perform better on, but this is definitely something that we've kind of tossed back and forth. Okay, and then could one naively use PacMap in lieu of PCA for dimension reduction? Yes, you absolutely can. And then if you do that, you'll get local structure in addition to just the global structure. Okay, so now I get to try to understand this more difficult one. Okay, Am I correct in interpreting all of these methods requiring only data that is ordered? No, the data does not have to be ordered. And that the difference between 2 and 6 has to be the same as the difference between 31 and 35. I do not understand that question. 31 and 35, what? And consequently, any type of factors or categorical data. No, categorical data is fine. You just encode it as ones and zeros. That's totally fine. Oh, okay. All right, great. Thank you. Cool. Did I get everything?
I think you did, except I have a question.
Oh, yeah.
So what did you, maybe you said it and I missed it, but what did you implement it in? I saw a little bit of MATLAB there.
Yeah, so it's in Python. We are trying to move it into R. We've been trying to move it into R for the past, a couple of years, actually. But we're having a lot of trouble because we want to use a really efficient nearest neighbor finder. And we're having a lot of trouble figuring out how to attach that to the R. And so so the students have gone back and forth. So one student spent a really long time in it, and she gave up, and she sent it to the other student who's now spending a really long time on it. So if somebody is an amazing expert person who can code R and C, then please let me know, and I'd love to talk to you.
Well, that's not
Cynthia,
me.
Cynthia, I'll just note that we did have some questions in the chat about the port to R. Can I pose a question about, kind of taking stock of available software? And I see some comments from Chuck Coleman about things like Julia. How do you approach a selection of software to implement these novel things, and what kind of experimentation have you have your students done and found effective or not?
Okay, wait, those are two separate questions, right?
Perhaps, yes.
Okay, so so which software to use? So we basically always use Python just because that's what all the students know. So yeah, I mean, if I had a student who was more comfortable in R, we would do it in R. Or if we were using a code base, like if we were starting from a code base that was already in some language, we would probably stick to that language. So it's a question of convenience more than sort of, anything else. And then, sorry, the other question was what?
Have you considered alternatives like Julia?
Oh, no, we haven't considered Julia. Yeah, I can suggest that to my students. Yeah, we could try that. Oh, ChatGPT. I don't think ChatGPT could handle this one. Yeah, it's really connecting these two pieces of code that we're having trouble with. But yeah, my students use ChatGPT a lot to help them with various coding problems. Yeah. I'm sure they're already using it for whatever they're trying to do. I think you asked me another question though, which was like, how do you investigate? What was the question? How do you investigate? How do you?
Yeah. Well, I think more generally, coming from a federal agency background, there's kind of the joint considerations of how well supported certain softwares are, and if there are any gains to be had working in one versus another. So you mentioned the convenience of the ready knowledge base, but if you had a staff who weren't already well trained in these areas, how would you approach the problem of trying to bring these novel methodologies to government data within those confines?
I mean, everything we do is pretty much in Python, so I don't really know. I mean, we don't even, to be honest, we don't actually think about that, and maybe that's something we should be thinking about more carefully. Yeah, and if you have suggestions about how we should go about thinking about that more carefully, I would be very happy to hear about those.
That's encouraging to hear, because one of the issues that we have in the government is hiring new people, bringing them in, and then what are the capabilities that they have. Of course, we could always train them, but it's good to kind of have an idea of what knowledge they have with respect to statistical computing. So but I noticed you didn't say SAS. So
Yeah. No.
There is another question in the Q&A.
oh, okay, good. Thank you.
Yeah, no, I haven't looked at, I've never even heard of Neo4j. Yeah. Maybe I should have heard of it, but I haven't. I'm sorry. It would be nice if, I mean, every once in a while we get somebody who's like, hey, I find this tool useful. I've converted it into this language. Here, why don't you post a link to it? And we're like, okay, great, so that's very helpful. But yeah, so it'd be nice to have more people doing stuff like that. Yeah.
I always think we need more more tools in our toolbox. Okay, well, we'll wrap it up. It gives us a few minutes to change over to our next session. Cynthia, thank you again so much for giving this talk. I always love hearing you give talks, and it was fantastic, and I'm going to start playing with it, except I don't really know Python, so I may have some trouble there. Anyway, thank you again, and hopefully I'll see you at JSM.
Yeah, see you at JSM.
All right, great. Thank you.
Bye.
All right, bye.